let's see this equivalent way. Let's rewrite this thing with its formula. So we have that our Lagrangian goes into L plus this Lagrange multiplier term. Then there is the n minus lambda over 2 BA, that is m minus 1 AB BB plus the ghosts Now, remember that lambda is a gauge fixing parameter. It's arbitrary. There is a particular case, which is lambda equals 0, which is called Landau gauge. Which you can use here because you drop that term. And then when you drop that term, the equation for B is the one that tells you that GA should be 0. So the gauge condition, if you can solve it, Landau gauge is very practical. Lambda equals 0 cannot be used very efficiently in the other form, where there is a 1 over lambda. But it can also there, because normally the Landau gauge is done there, actually. But if you want to make it neatly, just introduce this auxiliary field, and it goes straightforwardly. If you have a derivative gauge, you cannot solve the condition, but still you can use the Landau gauge. Simply you have to invert. This one is not invertible, because it's not gauge fixed, but if you add that term, that becomes invertible. For example, in QED, if you have minus 1/4 F mu nu plus B has no indices there because the gauge fixing has no indices. That can be used, just that, as a gauge fixed action. The ghosts will decouple, then there will be the same thing there. We know already that the ghosts are not important, but here you can have this is invertible for the multiplet made of A mu and B. So you can build a 5-component vector, A mu and B, and consider this as the quadratic action for that. There is no B squared, fine, who cares? It is invertible, and you will have a meaningful propagator, which is the Landau gauge propagator. We don't derive it here because it's something that takes us a little bit far away from our interests, but just to mention that this. So, for example, this Landau gauge is very useful for the symmetric gauge, for the field bind, because not only you can solve it, it's not like QED, like this case, where it has derivatives, so you build a larger multiplet. It's much simpler. Not only you can solve it, but this part is also algebraic and goes away. Not just decouples, it goes away. So symmetric gauge. So basically, you can say that your GA goes into phi mu A minus phi A mu. That's our gauge fixing. We want to impose that equal to 0. So you have that your Lagrangian will be a Lagrangian plus a multiplier, which will impose that condition. And you can drop this term by just saying f mu a will be symmetric. It's like solving this equation and inserting back the solution into the action, so you can do it. We write it down just because it's there. Symmetric gauge and Landau gauge, if you want. And then let's build that. There will be an anti-ghost with the same amount of indices as the gauge conditions. So let's write it like that. C bar mu A. And then you have to write the gauge transformation, this one, for phi. E is eta plus kappa, etc. Let's write it to the lowest order, because it's enough for our argument. So basically, yes, we have this and flat space expansion. Then, what do you have when you replace the flat space expansion here, inside the variation of delta L? Well, you will have delta L of phi A mu A equals ghosts plus higher orders. Why? Maybe you don't see it, but if I want to make the variation of delta, the variation of eta will be 0. So the variation of delta is the variation of phi up to a constant. But the variation of phi is to the lowest order the parameters themselves, because to the lowest order E is eta. E is eta to the lowest order. So the variation of phi to the lowest order is the parameters which I will call C, including the constants kappa and whatever. Okay, is this clear? You can do the stuff, but basically you just do this delta this 0 kappa delta, and here you put eta to the lowest order, and then you call theta a mu, because this will be theta a mu times 1 over kappa. You call it C. We will see why the rest is not important. All these corrections are not important. So let's do this variation and the multiplication. Multiplication for that is this, it's just C. And the variation is also simple, because it's phi. The variation of the gauge fixing condition with respect to phi is a delta. It's a delta, right? So the gauge fixing condition has two indices, which are, by the way, the same indices. Okay, now there is a problem here. I have to save it, maybe. Okay. Let's see if now we can work. Apparently not. Yes. Okay. So the indices big A are mu A, and the indices R are the same indices. So basically what you have is the identity. So what you have is delta mu delta A with new indices, which we will call nu and B. And so this delta C will have indices nu and B minus the antisymmetric part. Yes. Plus whatever, we will see that this is not important. Well, we can already say that it is not important. So basically, the first part you can get rid just by saying I solve the B field equation, and from now on I use phi mu A. I assume that it is a symmetric matrix, and that solves the Lagrange constraint. The second one you can drop because you see this is a constant, so this multiplies. C bar mu A is, although it has mixed indices, it has to be antisymmetric. With this we have not said, but this, you see, is antisymmetric when theta AB is antisymmetric, so we have to remember that C is antisymmetric. And of course, C bar is antisymmetric because it's the partner of C. How do you see that it's antisymmetric? Check here, the gauge freedom. It tells you that the transformation of phi, which is any matrix, is antisymmetric, arbitrary, which means that you can kill the entire antisymmetric part. Okay? So phi, in general, with no gauge fixing, is a sum of a symmetric part plus the antisymmetric part. The symmetric part is invariant, because the symmetric part is Lorentz invariant to the lowest order. The antisymmetric part instead can be shifted arbitrarily, so it can be set to 0. That's what this gauge transformation tells you. I don't know if you see it, but maybe you have to think about it a little bit more. So basically this is C bar times C plus whatever, but you can change variables and call the entire sum C plus whatever. You can call it C, new C. The change of variables is physically insignificant. So basically, this thing becomes C bar mu A, C tilde mu A, and the field equations of these are C tilde is equal to 0, C bar is equal to 0, so that's totally irrelevant. That's a way to say that the symmetric gauge is very, very nice gauge. You can just use it, assume that your field buying or your phi is symmetric, use it anywhere, and forget about any construction we have made about the gauge fixing, forget about the ghost part for the Lorentz symmetry. We have done that, all that effort just to convince ourselves that it was not necessary. Okay, this is a nice thing about this kind of particular kind of algebraic gauge. It will not work, for example, for the synchronous gauge. Nothing like that will be simple for the synchronous gauge. Where is it? Here. The synchronous gauge is algebraic, yes, but the transformation of G mu nu is not algebraic. It has derivatives. That's why, yes, it will be, you will have a simple part here. This will be very similar. You can use that Landau gauge, but the ghost part will be present. It will not be negligible. And actually, this gauge is kind of annoying to use, not only at the level of quantum field theory, but even classically. If you want to take anything, any problem you are interested to study and you want to see how it looks like in this gauge, you will see very, very awkward formulas. And that makes the synchronous gauge not particularly useful, but I have to mention it because it will come back when we will talk about the positivity of the energy of the gravitational field, which is a very delicate subject. We will not go through the entire proof, but unfortunately we will have to specify that the positivity has been proved only in this awful gauge, because there is no notion of energy for the gravitational field that is independent of the gauge, because the very same idea of energy of the gravitational field depends on the reference frame, the coordinates, the gauge, because there is otherwise no energy. There is not a stress energy tensor that you can define for the gravitational field. Another gauge fixing that sometimes is used for the field bind is as follows. For the local Lorentz transformations is this. So remember that the local Lorentz transformation of the spin connection was equal to a covariant derivative of the covariant derivative, apart from a minus, maybe, don't remember if I had a minus, of the parameter. So you can say, oh, this is very similar to delta A mu equals partial mu lambda, some indices around, but why not mimic the usual gauge fixing condition, partial mu A mu. So that would be this thing. So that would be our G Lorentz AB. And it does not break diffeomorphisms. This breaks only Lorentz. So this is the advantage. It does not break diffeomorphisms. And the disadvantage that it is a gauge fixing like the usual one, so it has derivatives and you have to work out more complicated formulae than the ones you meet with the Lorentz gauge. So by far the Lorentz gauge is the one that's preferred. Now we make other remarks about Weil invariance. Now recall that we have found that the Weil tensor has very nice symmetry properties with respect to Weil invariance. And if you write it in a certain way, it is actually invariant. Let me stress it here that the tensor that is invariant is the one with one upper index and three lower indices. If you raise and lower indices, you will have a certain transformation, because remember that G is the tensor that raises and lowers indices, and G transforms. If you want to transform the Filbine, that's why I put a 2 there, the Filbine will transform with e to the minus omega. So that is the tensor that is invariant. Three indices are low indices and lower indices, and then there is one upper index. If you lower the index, 4 lower indices, you will have that it will transform like G. Then we saw that there was an action that was invariant. The Weil squared action. Yes, I think it is here somewhere. We did not make any comment about the invariance of other actions. For example, what about the matter sector? Okay, don't find it here. Well, it's interesting to know maybe that basically all massless actions are Weil invariant. For spins 0, 1/2, and 1. Not for spin 2, Hilbert action is not invariant, and not for spin 3/2, even worse. Massless with the caveat that we will see all masses can be made Weil invariant for spins zero, 1/2, and 1. For example, the Yam's action, that's basically already Weil invariant. We have to supplement the transformational rule with the transformational rule for the matter field, and we are free to choose any transformational rule we want as long as it makes the theory invariant if it exists, and in this case it is no transformation at all. Because if F mu does not transform, you see that G inverse takes a factor e to the 2 omega, G inverse takes e to the 2 omega, and what about the square root of G? The determinant of G is 4 times this, so e to the minus 8 omega So the square root of g takes a factor e to the minus 4 omega. So that's invariant. In 4 dimensions only. That's a property of electromagnetic interactions, 4 dimensions. What about the fermions? So of course the hope to have a while invariant action is only with massless actions, with no mass, because the mass is a scale, and the gauge transformation here, the while invariance, is a local scale transformation, if you want. But the Dirac action is invariant. How should psi transform? Well, remember that E again takes a minus 4 omega, E determinant, I mean. Instead, here we have the field bind. The field bind gets a factor e to the plus omega. So what should happen to psi and psi bar? Psi should take 3 divided by 2 omega, and psi bar the same. Because this is a scale, transformation cannot make any difference between psi and psi bar. But if this is so, then you have at least invariance globally. Now the question is globally, which means with constant omega. That's an invariance. With constant omega, we have already verified it, because if it is a constant, it doesn't affect the, well, in flat space, let's say. Now, if it's a constant, it's immediate to understand that it is invariant even for the metric, because the Christoffel symbols contain as many g minus 1s as many g's. So the scale factor compensates. And the same for the spin connection and everything. So there is no problem there, it's really immediate. Another story is to show that this holds also for omega non-constant, but it does. So that's an invariance. I don't ask you to verify it, but it is true that something may become useful to know to you in the future. What about the scalar fields? Scalar fields have an action that is equal to the square root of minus g. Then you have partial mu phi, which is equal to, del mu phi is the same, g mu. And then remember that there is a non-minimal coupling that you can have also in the massless case. Well, for a particular coefficient, this is while invariant, and the coefficient is 1 divided by 6. If phi transforms in a certain way, we can determine how phi should transform, because, again, the square root of minus g is minus 4 omega. G inverse is 2 omega. and so phi should just get 1 omega. Globally, this works, and you can check that indeed globally R takes the same factor 2 omega. But what about locally? Well, the property is that R transforms as follows. You have to change the notation. It goes into e to the 2 omega times R plus 6 del for the squared omega minus 6 del mu omega del mu omega. If you want this something you can check. Actually, I would leave it, but probably it's the only exercise of the second part. So maybe this is worth to do because it's not so difficult exercise. And then you can show that this is invariant. Why? Because this exercise, we will do it here. SS goes into what? 1/2 square root of minus g e to the minus 4 omega. Then you have g mu nu then you have del mu phi goes into e to the omega phi del nu e to the omega phi plus 1 divided by 6. Phi squared goes into phi squared equal times e to the 2 omega. And R goes into that expression that we now have to add. Okay. But this is quite simple because you just have to take these two derivatives and sum those terms. One half integral of the square root of minus g e to the minus 4 omega will disappear because here it will be simplified by that in the second line, but also here because once you differentiate here, you will have the exponential will always stay out. So the differential of this, the derivative of this will be e to the omega times partial phi plus partial omega phi. So that factor disappears. So we get g mu nu partial mu phi plus partial mu omega phi. And the same there, partial nu phi plus partial nu omega phi. Plus 1/6 r phi squared, which is what we want. plus 1/6 times 6, so that's phi squared del squared omega minus phi squared del mu omega del mu omega. Okay, so now the first product here plus 1/6 gives back what we want. And that should be all. The rest should cancel out. And does it? This part, for example, cancels with this kind of product. Cancels. And this should cancel the double product. Let's see. So we have a double product, which means 2 del mu phi, del mu omega, phi, del mu phi, del mu raised phi, plus phi squared del squared omega. And that is 0 after a partial integration, because if you move one derivative here, you get a minus, and you get a 2 phi del phi del omega, which cancels that. So up to a total derivative, this is invariant. Don't have a lot of time, but for the future it will be useful to work out stress tensors, which we have not done so far. Let's do it in one case at least. Stress tensor of gauge fields. So stress tensor of gauge fields. This is the action. And we know that the stress tensor T mu nu is equal to twice 1 over square root of minus g. Then there is basically the Euler, the Lagrange equations of that action. So we find, we take the variation with respect to the metric tensor with upper indices because it appears twice with upper indices, and the square root of minus g we know. So what you get is, so 2 minus 4, 1/4, So 2 this 4 disappears because you have a 2 there, but you have two terms that give the same result. The square root of minus g also disappears, but we have a minus. We have to take care of the minus. So we have minus f mu rho so when we take, okay, the first two indices should be the free ones. Yes, like that. And then there is the variation of the square root of minus g. That is equal to 1 divided by square root of minus g times 2 times the variation of that, since we are varying respect to so we get minus 1 half square root of minus g mu nu. Yes. So that would be equal, there is only a minus sign, 1 over 4th g mu nu f squared. That is, notice that t, the trace, is 0. Well, we won't get the chance to get into the details about this, but the trace of a stress tensor is the thing that governs the invariance under scale transformations. In this case, Weyl invariance. We have already seen that the theory was Weyl invariant. That means that the stress tensor had to be traceless. And similarly, there are traceless stress tensors. You know that stress tensor can be redefined adding total derivatives and things like that. So there is not a unique definition, but it is important that there is always one that is traceless. In this case, it's the first one that you get just from this definition, but it's given by the Weyl invariance. So that was guaranteed. Okay, we can stop here today.